Okay, guys, let's get started for today. So, what did we talk in last class? What did we talk about? Motors. So, in our system, we talked about we have a microcontroller, which is the Pi, and we talked about there is a different sensors. We talked about how to digitize the data, right, through ADCs, and we connect to the microcontroller. And if you want to take an action on an actuator, we talked about the different types of motors, yes? Okay, we talked about that. But one thing we have not talked about is, come on, what kind of interface do we have? Like when we're talking about these connections here, especially between the sensor and ADC, or the ADC and the Pi, you connect a wire, okay, and you pass data, right? Sometimes it is one wire, sometimes it is 4 wires, sometimes it is 10 wires, or sometimes it is only single wire. So when we send data on here, you got to follow some particular protocols, some particular standards. And so what are the different standards here? What are the different protocols is all we are focused on today. So wired communication protocols, okay? So let's see what we have here. So if you're connecting like to a desktop and a embedded system like a microcontroller, how do you connect? What do you do? If I'm taking a Pi or let's say an Arduino to a computer, what do we do? How do you connect them?
Wires.
Wires? Can't you do wireless? Arduino and computer? So you do wired or wireless, right? I mean, there is 2 modes possible, yes? Wired or wireless. In wired, you typically use USB, yes? USB is one mode of communication. If you want to do wireless, you can use what? Wi-Fi or Bluetooth, typically, okay? This is pretty, because most of the computers, and they have built-in USB ports, and they have built-in Wi-Fi, they have a built-in Bluetooth, pretty straightforward. But when I'm connecting this microcontroller, okay, a peripheral, let's say a motor here, right? Or it could be one of the sensor, right? Can you use a USB? Like for example, we have the ADC sensor that we had, and the ADC to the microcontroller. Did we have a USB going on? Did we have a wired or a wireless connection going on? No. Do you guys recall how many wires we had when we from the ADC to the microcontroller? 4. Yes, you're right. You're absolutely right. So we have VDD, the power line, then we have the ground line, and data and clock. Okay, we had 4 different lines, and we were using one protocol called I2C, integrated circuit, or sometimes it is also written as I2C. Okay, that is one type of a protocol. Okay, and there are different modes of them. So we're going to look more into what are the different types here. Okay, so when we talk about these, right, I mean, when we're connecting more systems to the microcontroller, if I'm connecting 40 different devices, okay, 40 different devices to a microcontroller, the easiest way is, the simplest way is adding, like if you have a microcontroller, it has different pins, right? It has different input-output pins, yes? Now, if I have only 8 pins, basically I can connect 8 different signals to the microcontroller, right? But if I want to connect 40 different signals, then I need 40 different pins, yes? So is having more pins better or not better? Better? I mean, on the outside, yes, It looks nice. We can have more systems. But think about this. Look at this physical size here. I have only 8 pins here. And if I want to add 4 more, I can do only 16 till here. Yes? Now what do I do if I want to have 40? Make the pin smaller? Yeah, I can make the pin, you're right, make the pin smaller, but I can make it smaller only as thin as a wire. Yes? I mean, if the wire is, if the pin is the size of a micrometer, can I connect a wire to it in a stable fashion and have it stable? No, if the pin is only like this, the wire is this thick, right? Potentially. If I have one pin here and one pin there, one pin there, one pin there, one pin there, and the wire is that thick, can I distinguish between two signals? It becomes hard. What do you do then? Smaller wire. The wire can be only so small. Then you basically do the opposite, which is make the device bigger, right? So you got to space these pins apart. You got to space the pins apart, farther apart, and when you make the pins further apart, what happens to your silicon size? Larger. Silicon size is larger, and your device size is larger. And your device size is larger, your power consumption is larger, and your battery usage is higher. And the lifetime of your device, battery lifetime, is going to be lower. So good? No. So ideally, you want to minimize the number of connections we have, okay, is what we're going to look into. So when you're selecting wired communication protocols, you got to ask all these questions, okay. So for example, when we did the ADC, we did the I2C. That required 4 wires, right? Then there is different protocols, something like SPI or something like UART, okay? And this requires only 2 wires. This requires only 2 wires, okay? Sometimes more is better, sometimes less is better, okay? And are we going to send it synchronously and asynchronously? What is the difference? Synchronous versus asynchronous. Yeah, it's with respect to, the same time or at a different time. So when we say asynchronous, I can send in random order with no particular order per se. So I can send the first signal at 1 second, the second one at 2 seconds, the third one at 4 seconds, 5 seconds, 6 seconds, doesn't matter. I send them in random order. But if I'm doing synchronous, I'm doing it with respect to a particular signal, maybe the clock signal. Every first positive clock edge or every second negative clock edge or something with respect to something, asynchronous, okay? And how fast can it transfer data? Is it important? Is data transmission speed important at all? Let's say if you're live streaming video, okay, if you're live streaming, do you need to process the data and stream the data quickly, or can it be slow? Fast as possible, right? Sometimes, okay, can we send it to more than one person? We're acquiring the data, but if I'm having a sensor here, I'm connecting it to the ADC, and from here, do I want to send it to only one microcontroller, or do I want to send it to a second microcontroller? And both of them are going to do different actions, okay? So, and then, do we want to take information back? May not be on the ADC, but something else, some other system. When you're doing wired communication, you want to have information going both ways, or just one way. Or how does it handle noise? For example, if you take a system, you design an embedded system and put it right next to the engine block of a car, would it be okay without any shielding? Yes? No. Why not? It's a harsh environment. The temperatures are high. The noise is high. right? There is lots of vibrations, lot of different things. So can the communication protocol handle all this? So you got to learn, identify all these factors. Okay. So with those factors, let's see what are the different modes. The first one is parallel, okay, and serial. The difference, what is the difference, guys, between between parallel and serial? What is the fundamental difference? Say that again. One off and multiple off? Okay. Uh, that is the, you're right. I mean, in a series connection, if something goes wrong, it's a ripple action, and everything potentially, it's cascades and everything will go stop. In parallel, might not be the case. But what is the fundamental difference between serial and parallel? Yes. In, like, for example, here, look at this data here, guys. I mean, the top one, what I have here is I have B0 through B7, total 8 different data points. Okay, I want to send 8 different signals. So basically, in parallel, I can send 8 of them all at once. Okay, from one device to the other, all at once. In a serial, there is only one line. Okay, and I have to send one after the other after the other. Yes, sir.
What's the difference, I guess, when it comes to computer, like, science, I guess, with the hard drives then? Like, is there a difference because they have SATA and SATA? Like, wires?
SATA is, again, it goes into the serial mode, but PATA, I don't know what PATA is. But I can look up and I can tell you what that is. SATA, I heard SATA, but I don't know.
It's older, SATA.
Oh.
It might be like floppy disk here, but like.
Let me get into the, I'm not familiar with the architecture inside, to be straight with you, of the hard drive. So
I was just wondering if you might have, like, been able to make, like, an analogy or something with this. I don't know if it's the same or not.
Analogy, okay, I'll put it this way. Like, do you guys remember the old parallel huge ports on the computer to hook up printers? Do you ever see them before? We used to have like 25 connectors, 25 pin connectors for the printers back in the day. Those are like literally like parallel, what you see on the top here. And then we moved on to the serial like 9 pin connectors and RS-232, and then we moved on to the USB. USB is purely serial. Okay, the parallel ports is the 125 pins that is all parallel there. To give you an example of progression of where we were. I mean, parallel was good when the throughput was not high on a communication channel. But now, in the USB, for instance, you can do up to 650 megabits per second on a USB. Okay, a single line. There is a single line on a single line, you can do 650 megabits per second. In the past, that was not even remotely possible, not even on Ethernet back in the day. So things progressed, so we are moving away from parallel to serial now. Does it give you an answer?
Yeah, that's a great one.
Okay. So now, here is my question here. So in parallel, we can stream multiple data points at once, right? But we need more wires. Okay. In a serial, there is only just a couple of wires. One is the clock, the other one is the data point. Okay, so which one is better for microcontrollers? For what we want to do? Let's take the scenario in this class. Like, okay, I'm not talking about every possible scenario, but in the realm of IoT, what is good? Serial or, which is better suited? I'm not saying which is good, but better suited for microcontrollers. Serial? Why?
It's smaller size to connect with microcontrollers.
You mean this one? This one is better? So you have more.
So it's a smaller size to connect with microcontrollers.
Yes, I mean, on the microcontrollers, like not, let's not take the Raspberry Pi for instance, right? Most of the real world IoT systems, microcontrollers are pretty small. The number of pins they have is very limited. The resources are very limited. But the speeds are relatively high. They can do few megahertz communication speeds on each channel. But if you talk about simple sensors, if you keep the camera aside for a second, right? Camera aside, light sensor, temperature sensor, pressure sensor, all these, and even accelerometers, do you need to take 10,000 samples per second at all? In real world, I mean, most of them, you don't need that many samples. Maybe you need maybe 1,000 samples a second, maybe, at the most. You don't go beyond that. So when a serial can do all what you want, it can do one single wire. The microcontrollers, most of them have 2 pins easily, and they can support up to a few megahertz. Why go with parallel? Okay. So think about along those lines. I'm not saying it is the case every time, but most of the time here. Okay. So now here again, in terms of serial, let's talk about serial here, by the way. And in terms of serial, we have synchronous serial, we have asynchronous serial. So again, synchronous serial is we have a clock signal. Okay, we have a clock signal, and you have your data. Okay, and the data changes probably at every particular clock edge. Like maybe you changes every negative clock edge, every falling clock edge, or every other falling clock edge. Okay, versus this one is synchronous, right? So then if I do asynchronous, I'm doing data sorry guys, it changes in random order. There is no particular order. You can send data at any given time. Okay, this is more on the asynchronous one. And asynchronous, the fundamental, the mostly used is UART communication. We will talk about more in there in a second. And synchronous is more I2C. The one we used for ADC the other day is this. The one we use is this. Okay, and on Thursday when we come back, we'll do a lab on I2C again. Now, here is one other few other points we got to be familiar with when we're sending data. Okay, so we got to think about like how fast are you sending the data, right? So for example, I will say this in general. If I'm talking at twice the speed or 3 times the speed, and the other person is not able to comprehend that speed, will the information or the message be conveyed to the other person at all? Or like say for example, like you're all electrical engineers, I'll put it this way. I will stream data at 2.4 gigahertz signal and at 2.4 gigahertz rate, and you're looking for data to read at a rate of maybe 4.8 gigahertz, just making a random number. Would you be able to comprehend the data at all if you're on a different band? No, right? So we have, remember this guys, see here, when I said serial, there is one clock signal, right? And then there is one data line, yes? Yes, you all with me there? So here is my point. if I'm sending, this is my sender, right? And I set my clock rate as 2.4 gigahertz, for example, okay? And on this side, this is the receiver, right? And on the receiving side, I'm trying to receive at 3.6 gigahertz. If I send all my data, will I be able to read the data properly on the receiving side? No, right? So here, there is something called baud rate. Did you guys see the word before? Maybe when you're using Arduinos? Yes? No? Baud rate specifically says how fast am I sending data. It's a simple thing, like I will show you in a graph in a few minutes. We are trying to say, and here I'm saying I'm sending data at a rate of 2,400 gigahertz range, in that speed. Like for example, the ranges are, I'm sending 1200 bits per second, 2400 bits per second, 4800, 9600, 19,200 bits here. We have the communication between the sender and the receiver at the same baud rate. Okay, the baud rate here should be equal to the baud rate on the receiver. Okay, so if I'm sending here on the sending side at 1200 bits per second, and if I'm trying to receive it at 9600 bits per second, the message is not conveyed. It's not encoded and decoded properly, and then the whole message is lost. Okay, so the key here is the transmitter and the receiver should have the same baud rate. Okay, remember that all the time, especially in serial communication. You have to trigger that. So if you are playing with Arduino, the simplest way to try this, the simplest way is take a simple Arduino, print random data to the serial monitor. Okay, in the Arduino, set a baud rate of 9600 or something. Go into your computer ports, into that port, read at a different rate, and try to see the serial monitor. Okay, you might be sending 242 some data points, and you might see special characters. You might see special, fancy, weird characters on the serial monitor. Okay, if we set the baud rate on the transmitter and the receiver properly, you will see the same. You will see the same 242 data points. Okay, so we will play with that probably in a week or two here, slowly. Now, if you're sending serial data, right, there is a few rules that you got to follow. There is, you got to say when you're starting. You have to say when you're starting. Then there is, you have to send the data. Then there is parity bit. Then there is a stop bit. So anytime you're sending data, something like 242, for instance, a random data, or if you're just trying to send, maybe you're not trying to send 242, you're just trying to send 2. Okay, you got to have the start bit here, then you have to have the parity bit, and then you have to have the stop bit. All of this together becomes your data packet. Okay, all together forms your data packet, and you have to encapsulate all this together. So the start bit and the stop bit are just primarily just 1 or 0. Okay, it all depends upon the communication protocol you're following. It could be a 1 or 0, but it's only like 1 bit. And the stop bit, it could be 1 or 2 bits. If it is 1 bit, it could be 1 or 0. If it is 2 bit, 0, 0, 0, 1, 1, 0, 1, 1. Okay, it is a stop bit. It all depends upon how you write your program. Then parity bit. So parity, guys, tell me if you guys remember parity. And what is parity? So, anybody remembers this or no? That's okay if you don't. No? Okay. So, we do send lots of zeros and ones, right? The data we send, if you see here, look at this here. We do send a lot of zeros and ones, right? Sometimes there could be a problem in the communication and the wrong message could be delivered. Okay? Parity is the simplest way to make sure, simplest, not often the foolproof, but simplest way we can make sure the right data is communicated. And simply, we can say, if I'm sending lots of zeros and ones, and the parity bit can say, how many ones am I sending? Am I sending an odd number of ones, or am I sending even number of ones? Okay, it's a simple device, it's a simple logic here. So we have odd parity. So if your data packet, for example, is this, for example, okay, how many ones do we have here? 3. Is it an odd or even? Odd, right? So let me rewrite that, for example, guys. So this one, 0, 1, 1, 1, 0, odd, right? So it's odd number of ones. So if you're using odd parity, this becomes a 1. Okay. The same thing here. If I'm using even parity, okay, if I have even number of ones, the parity bit is 1. But for this data, do we have even number of ones? No, right? So we set that as 0 here. Okay. So you add the parity bit to tell the receiver that, hey, you're supposed to receive odd number of ones or even number of ones. Okay. So is that good or bad? Good, right? I mean, if there is one data, for example, so let's say this data goes wrong, okay, you're supposed to have odd number of ones, and you get a 0 there, you know you get even number of ones, and you can identify the mistake. Yes? Good so far? But what happens when this happens? You're supposed to get, let's say, even number of ones, and your 2 data points go bad, and you still get 2 even number of ones. Can this parity bit help? No. So the limitation of parity bit, what is the limitation of parity bit? Only data loss of 1 data point, or odd number of points. So if you have data loss in odd number of bits, then it is okay. So 1 bit if you lose, 3 bits if you lose, or 5 bits if you lose, maybe you're okay there. But primarily the most fundamental, if you lose more than 1 bit, parity doesn't help at all. Okay. So now coming back, I want to show you something here fairly quick. Here is my data packet. Here is my data packet, guys. I want to send, here is my data. This is my baud rate. My baud rate is 9600, and I'm saying my number of bits I'm sending is 8 bits and no parity. Parity bit is purely optional. I don't care about parity. Okay. Then my stop bit is only 1 bit. Okay. And my data is okay. That is my data here. And see what happens here. Okay, right? So okay are characters. So when you transmit everything, the data get changed to the ASCII value. The ASCII value of O is 79. 79 in binary is that number. Okay? Now, same thing with K here. See here what happens. Your start bit is 0. Now, tell me, okay, right? So it is supposed to read 0100 1111 0100 1011. From here, at least the first 8 here. Is it reading this data or this one? Look at what's happening there. My data here, from here to there, it is supposed to send O, which is 0100 1111. Bingo. See what happens there. The data is not sent as it is. It first sends the LSB, and then lastly it sends the MSB here. Okay, so you have your start bit, you send O, which is 1111 0010 in the reverse order, and your stop bit. Stop bit is only 1, right? So this is your stop. Then O is sent, then the K. Again, you start from here, go the same way here. Okay, start, data packet, stop. Start, data packet, stop. That is how you typically send data in serial transfer here. Always LSB first. Least significant bit. Yes. Okay. Now. Oh, come on. So, okay. So when you're trying to do serial, all we need is 2 sides. Let's say this is unit 1, and this is unit 2, and I'm sending from the first one to the second one, and the second one sends to the first one, right? You need 2 wires. Simple. Now, my question is this, guys. Is this line important? The one in yellow. The one I just highlighted, the ground line. Is it important at all? Yes? No? Why? Why do we care if it's not on the same ground line? What happens? What happens if they're not on the same ground line? Your reference is off. Some of them might be operating at maybe negative 3.3 to 3.3. The others might be operating at 0 to 3.3, and your whole references goes off, right? So whenever you are connecting 2 different devices, especially from now moving forward, remember this: all the devices, the hardware you have, make sure you ground them all together. If it is 2 units, 4 units, 5 units, 10 units, all the grounds have to be connected together. Okay. Most often, most of the problems I see is to do with ground. It's more than you think. So you got to have all this together. So now we have 2 different types. There is full duplex and a half duplex. So if I'm sending information only one way, that is a half duplex. If I'm sending information both ways, okay. So in this case, unit 1 is sending to unit 2, and unit 2 is sending to unit 1, right? So what is this? Full duplex. Okay. So would we need full duplex all the time? Or would half duplex suffice? And see here, we have 3 wires, right? So sometimes maybe I don't want wires. Sometimes only as a company, as a designer, you got to make sure that the number of problems you face is minimized. At the same time, you got to make sure the company saves money. So for me, if I look into here, if 1 less wire means less troubles and more cost savings, I would go that route. I would get rid of 1 wire. So can you think of any application where we need only 1 wire? I mean, only half duplex. Any thoughts? What's that? If you're just doing a simple display, or if you're just doing a simple turning on the motors, right? And if you're just doing data from a sensor cannot take any action. It can just provide you data. That's it, right? Do you need full duplex there? No. So remember that in mind. You don't need that all the time. So here, a couple of quick points. I mean, for you guys, I'll make this very quick. TTL logic. Are you guys familiar with the TTL logic? TTL is transistor logic, which is what we use every day right now. Okay, it operates at a 0 and high. If you see the range between 0 and 5 or 0 and 3.3, most of the ICs we use now are TTL logic. Okay, low voltage, the lowest potential is 0. The highest potential could be anything, 0 to 5 or 3 or 1 or whatever it is, right? TTL logic. RS-232 are legacy systems here. We have many legacy systems where the potential is not 0 to 5. Look at this range here, guys. On the RS-232, look at on the bottom one, look at the range here. Sometimes it is negative 13 to positive 13, negative 25 to positive 25, negative 12 to positive 12. Okay, and this is relatively good if you're doing long-range serial communications. Like for instance, like, do you recall your old telephone lines? Not your cell phone, the landlines that we typically have, used to have at least. How do they communicate? I mean, do they have electrical signal there? I mean, you don't typically give them additional power. Just pick up the phone and it works, right? And these cables are long, and they still work. They use the RS-232. They have a high voltage swing there. The current is very low, but the voltage is relatively high there. If you ever take a telephone cable and measure the voltage, you will see a high voltage swing there. Okay, but since the current is so low, it doesn't do any harm at all. It is probably in the milliamps, so it should not worry much at all there. Milli or microamps there. Okay. Now, so UART. Let's jump into UART fairly quick. So UART is all about. I mean, this is primarily UART here. This what we have here is a simple UART system, RX, TX, TX, RX, and a ground line. Okay, and UART, what you can typically do is most of the microcontrollers have a dedicated hardware. So you might have different microprocessor, and it can take all the data lines, your control lines from the microprocessor, and generate this RX and TX on your microcontroller. Okay, so like your Arduinos, Raspberry Pis, they typically have RX and TX. Okay, and the nice thing is, even if you do not have the hardwired UART module, okay, you can do all of what we are saying here. So here, all what we are saying here, take the data, send data in a synchronous fashion, time controlled, all of this. You can do, write a program, a software program, and do that entire serial communication without the UART device. And that is called bit banging, is what they call it. So if you have zeros and ones, so you can just put 1, 0, 1, 1, 1, whatever you want. You can put it all together as a packet. You can write a program, send the data 1, wait for time, send the data 0, wait for a delay, send data 1, a delay. You can easily control it. Okay. And if you're using Arduino or Raspberry Pi, so basically when you have your GPIO pins on your Raspberry Pi, okay, you can make it work as UART. So you have several GPIO pins, all of them, you can make it function like UART devices. Okay. You don't need 20 different UART hardware to communicate with 20 different hardware outside. You can take the pins, program them as software serial, and boom, you can start communicating. So here is the point, guys. Look at this one. Oh, come on. The figure on the top right is what I have here is a simple system. I have two devices communicating with different baud rates is what I'm having here. This one here. This is my terminal. Can you guys read anything there? I'm trying to see. Maybe I can see an XY there. Maybe a 30. There is maybe an alpha sign. Maybe 30 degrees here. Something. But you cannot make this out. This is what happens when you have different baud rates. Okay? So make sure your baud rates are accurate. Now, so we talked about we have a sender, right, or unit 1, and you have a unit 2. We said we can send data both ways, yes? But what happens if I add a unit 3? Can I tap this here? Can I tap this there? So basically I'm saying when I send the data here, but also send there. And if I want to send T3 to T1, do it that way and also do it that. So this is a major problem. Okay. When you're doing UART, you can only have one sender and one receiver. Okay. You can do only that. This, having two transmitters and one receiver, or one transmitter and two receivers, okay, theoretically speaking, and then occasionally it might work, but majority of the time it doesn't. Okay, because for example, you're trying to send data here, and this one is also trying to send data here. Which one should it receive? It doesn't know. Or you're trying to send data here, right? And you're also trying to send data here. Okay, and this data is meant to be for receiver 2, but by mistake it goes even to receiver 1. How do you do that? Okay. There is several problems there. UART, you can do only this. Okay. Same thing, same transmission speeds. We talked about this briefly. So let's jump into here. Yes. The next one is this, guys. UART we have seen, right? And if I'm trying to have only one sender, see here, I have one sender and I have one receiver, right? So when I have only one sender and one receiver, do we need 3 wires? Yes? No? No, we don't, right? One wire would just suffice, yes? That is basic serial communication, right? So let's move forward into here. There is a new interface after UART that's called SPI, Serial Peripheral Interface. So basically you have one clock line, making sure that you both are at the same clock signal. The other one is just simple data. Simple data here. Simple peripheral interface, right? 2 wires. One is the clock, the other is the data. Simple enough? Right? And the nice thing is, the both are at the same rate. You can send data one after the other, one after the other. It is as simple as it gets. Okay. And now, as I said, since it's simple, all what we need is a shift register. Take the data, push the data. Take the data, push the data, right? But what is the limitation here? Is there any limitation here in SPI? Guys, any limitation here? there is only one data point which, by this architecture, I can send only one data point. Yes. Now, but here is the point. Most of your cameras, for example, your Raspberry Pi cameras, which are pretty high resolution cameras, they interface with the microcontroller using the SPI. And they're pretty high resolution. They take a lot of data, but how? How does it work? This has one single wire, but I'm saying cameras uses SPI. How do they work? This is by default, guys. This is by default serial communication, but you can make changes. What changes can you make to this? There you go. So if you have a simple camera here, right? So you would get a still picture with maybe 1024, let's say 1024. I'm just making it up. 1024 pixels by 1024 pixels. Yes. So all these are digitized data. Yes. And these are actually inside. These are all numbers. These are all different numbers. Yes. So if you have all these numbers, you don't have to send the numbers one after the other, right? You can send a stream of numbers in parallel. You can take this, probably can say, I'm going to send all this first column in one line, maybe the third column on a different line, maybe the fifth column on a different line. Possible? So basically, I have one more data line, one more data line, one more data line, one more data line. Is that possible? They are using the same frequency. So basically, I take my data, split my data on the hardware side, transmit it, and on the receiving side, I take all the data, add it together, and I have my image. Simple interface. You can do very fast communication with SPI. But here is the point. Here is a simple problem with this. The limitation is that since we are doing high-speed communication, it is suitable for very short distances. So we're talking about less than a meter, less than a feet even. If you're doing high-speed communication, like cameras, high-resolution cameras, so if you see the ribbon cable on the Raspberry Pi is only about 4 or 5 inches because of that. Okay. If you make it further, it might take some more time, and the resolution might be going down. So, and also the cost, wires, right? Now, any questions so far? Or is it good? Guys, are you getting it so far, or yes? Okay. So here is a couple of other points here. In SPI, we have seen only the one transmitter and one receiver, right, going one way. You can do, if you want, you can update SPI to have two-way communication. So here, one is called a master, the other one is called a slave. Okay, so you have a clock signal. Okay, now if you guys can read this for a second, look at here, guys. Master and slave, right? Master, MOSI on the left side. MOSI is master out, slave in. Master out, slave in. Look at the direction of the arrow. Where is it going? From master to slave, right? And the other one, master in, slave out. Master in, slave out. Look at the direction of the arrow, right? So you can have two-way communication between master and slave using this method here. Okay? So now, is it a full duplex or a half duplex? What is it? Full. Yes? Now, this is great. Now, my next question is, can we add more slaves? In reality, let's say, for example, let's take an automobile for a second. Simple, if I take my automobile, and I have my dash, I have my center console, I have most of the cars right now have a nice 6-7 inch display that can display lots of information. So sometimes I want to see my radio there, sometimes I want to see my CD player, sometimes I want to see my maps there, right? Sometimes it shows maybe the compass. So basically it connects multiple devices to the screen, okay, not just one. So can we do something like that here for this one, SPI? Yes? No? Actually, you can. So here is the point. We have one slave, right, in this device. So here I add a signal called slave select. Okay, I can send a signal. Okay, so basically I have this. I have one master and multiple slaves. Sorry guys, I'm trying to. I have one master and 3 slaves here. So here, see here, master, one clock is shared among everyone. Then I have master out, slave in, master in, slave out, right? Those two are common. But if I want to select information from slave 1, then I have to enable the signal. Slave 1 I enable, then it goes here, it activates that device, right? Then I can go this way. Okay. But during this time, see here, when my SS1 is enabled, I'm communicating between master and slave 1. Now, at this time, can I send a new data packet from slave 3 on master and slave out, or on this line, master and slave out? Can I do one data packet on the yellow line here when I'm communicating between one master and slave 1? No, that is very bad, right? So by default, what happens is when I send a SS1 as a 1, you do SS2 and SS all the way to SSN as zeros. So you're telling that the devices don't communicate, just stay put there. Okay, that is one way. Or one other way you could do is daisy chain them together. If you see here, I have multiple SS lines, right? But look at the bottom one. I have only one select line here. So this line is shared among everyone. Okay. So on this line I will say, hey, I'm going to talk about to slave 2. Okay. And slave 2 will wake up, and slave 1. In order to reach slave 2, I have to first send data here, goes to master or slave in, then that information has to go out here. See here. And if it has to reach device N, then it has to go all the way one after the other, after the other, after the other. So, which one is better? Second one? But if I have 10 devices, if I want to communicate with the 9th device, it might take a while. So the response time to device 9 might be 9 seconds, and the response time to device 1 is only 1 second. And we don't like that. We want to have uniformity there. Then if you go to the first one, the response time is the same, but the hardware size is huge. You see that? There is no best solution for everything. So it all depends. Okay. So how do we minimize this? Is the next problem. SPI has this problem. But actually, there is this is what we're talking about, slave function, right? There is a different protocol here. It's called I2C. This is what we have here, which is what we use here. Here, by the way, if you see there is clock line, there is data line, right? And by the way, they also have high power, VDD, and there is ground. Just to make it simple, I did not draw them here. But the data is two lines here. One is the clock, and the other is the data. And the nice thing about this protocol is I can connect hundreds of devices on the same two clock lines. Hundreds of them. I can have multiple masters, multiple slaves. They can switch roles in real time. And maybe this can become a master, and this can become a slave anytime we want. And all just based upon two lines here. Okay. So let me show you what we do here. So we have a clock line, and whenever the clock goes down, you can push the data on the line. Okay. Whenever is the clock going up, you get a new data sample. Okay. But this is a simple data. But before you, on this data line, you can set information saying that, hey, I am master 1, master 2. I'm communicating with, maybe let's make this, 3, 4, 5, 6. Let me rewrite this, guys, here for a second. So each device on the network is going to have a number. So on the data line, you can simply say, hey, I'm device 1. I'm trying to communicate to device 5. Okay. So this is 1 to 5. And the 5 wakes up and everything else goes into sleep. You can communicate 1 through 5. Once you're done, 6 can say, hey, I'm trying to communicate to 2, maybe. Okay. And I can send it to one way or the other. Simple I2C protocol. So, and here the nice thing is, as I said, I can connect hundreds of devices, hundreds of them. So, overall, what do you guys think? Which one is better? I2C, SPI, UART? Let's see. Again, this is one other architecture I was showing you here. One master device can have multiple slaves on the same bus. They all share the same 2 wires here. So here is one point I want to show you quickly. If you are trying to pick different communication protocols, UART, SPI, and I2C. Okay. So it all depends upon if you want asynchronous or synchronous, if you want cost, do you want scalability? Like, what do we mean by scalability? So we built a system right now. I can work with maybe 1 master and 3 different devices right now, but tomorrow I want to come back and add more features to it. So I want to add more hardware to it, is what we're talking about, scalability. How do we scale it to add more bells and whistles? So with UART, can you have scalability, guys? In UART, remember this. You're doing you only 2 devices. Can you scale it to more devices? No. With SPI, how about with SPI? With SPI, remember this. If you have 1 master and 1 slave, and you have 1 more slave here, right? When you have multiple slaves, you need to add the slave select line 1, slave select line 2, slave select line 3, right? But let's say the master, the pins, there are already only 4 pins. You're using only 2 devices now, but you can scale up to 4 devices. But what happens after 4? Can you scale it further? Probably not. How about with I2C? There are only 2 wires. All you need is the new device to have a unique name or a unique number. That's it. As long as they have a unique number, boom, you can add more to I2C here. Okay. Now, that is done. So I'll ask one simple question for you all. We see UART, we see SPI, we see I square C, but where is this? Where is that? Or maybe, let me write on the top. Oh. Where is this one? Oh, sorry. I did the wrong one. Where is that? Why did we not talk about USB? You know, what does USB stand for, guys? Universal Serial Bus. It is a serial, right? Serial connection. Why did we not talk anything about USB? USB is good. It can do high transfers, but when it comes to this low power electronics, right, you need something that is portable. USB can go point to point, okay? But if you're trying to add 40 different devices, 50 different devices, you need additional hardware, okay? You need hubs. You need different protocols for all that. And that is like much larger in physical size than any of these. UART, I2C, and SPI, okay? Is why you don't do that yet, okay? Good? Okay. With that, we will stop right now.